Hello everyone, welcome to Code Enzyme. This is the 12th video of the series Graph Algorithms for Competitive Programming. And actually I wanted to make this video on minimum spanning trees, but I thought I should discuss the DSUs first because we will be using DSUs to implement that. Okay, so in this video we will discuss disjoint set unions. So basically the foundation for disjoint set unions. And before starting this video, I would like you to hit that like and subscribe button. And if you actually found this video helpful, kindly comment something in the comments so I know that this video actually helped someone. What is disjoint set unions? So I will denote it by DSU because that is the most common name that is used for this data structure. Okay, so basically we want to maintain a collection of disjoint sets. The definition goes like we want to maintain a collection of disjoint sets, right? And what is the collection of disjoint sets? Basically we have a set A, this is a set 1, this is a set 2, this is a set 3, and this is a set 4, and so on. Let's say we have set n. Okay, so I can these are set of numbers basically. You can imagine these as boxes. So there is a box on which 1 is written. Okay, there is a box on which 2 is written, and there is a box on which 3 is written, and so on. Okay, so you can imagine these as big boxes which can hold any number of items in them. Okay, so these are this is what it is. And like, how do we even identify a box? So there is some label written on them, right? And the most common way to identify the box is we can simply label them as one of the elements that is inside the box. Okay, so a DSU is something like, what we do is let's say we have a box with a number 1 in them, the second box is number 2, the third box is number 3, and the fourth box is number 4, and the nth box is number n. Okay, and we want to support operations like, okay, I want to join these two boxes. So this will create, if I will have actually two functions. One is the find function and the second is the join function, or merge. I can say merge. Okay, so merge box 1 and 2, something like that. Okay, so if I call merge 1 and 2, so a new box will be created with 1 and 2, and now I can label this box as one of the numbers in them. So I can say, okay, let's call this box as 1, like that. So this is the basic idea. We have the find operation will tell me, let's say I merge some of the boxes. Let's say I merge box 1, 2 and 4. Okay, so now I have some boxes. Let's say we have a box with 1, 2 and 4 in it, and the label is, let's say, 2. Okay, there is a box with 3 in it, the label is 3, and the rest of the boxes have labels. Okay, now the find operation is basically, I will ask which box, for the find operation I will ask, find 1 will just return me 2. I'm simply asking which box has the number 2 in it. Okay, so this will give me the box with label, it will give me 2. That means the box with label 2 has this number in it. Okay, so I will even write that down for you. So the operations that we want to have is, first is the find operation. It gives me which box has X. So this basically gives me the label of that box. Second is the merge operation. So merge X comma Y. Okay, so this gives me it doesn't returns anything, so this will be a void function. Basically it merges the boxes which have X and Y in them. Okay, and we want to do all these things in so we want to have merge operation in big of 1, and we want to have the find operation in big of 1 or log n time, something like that. Okay, so that is that. Now I want to give you the intuition for this. Let's say we have something like, okay, let's say I only consider for 5 elements. So we have the first box, the second box, the third box, the fourth box, and the fifth box. Okay, and let's say the first thing I'm saying, okay, let's say union or merge 1 and 2. So currently now I can store the box label as pointers, like okay, the box with label 1 was pointing to that itself. So the box with label 1 had 1, the box with label 2 had 2, the box with label 3 had 3, box with label 4 had 4, box with label 5 had 5. Now clearly if I want to join 1 and 2, I don't need to actually delete them. What I will do actually is I will point one of the numbers. I can take any of them, right? I can take 1 and point it to 2. So the new thing will become like this and this. Let's say then I do union 3 and 1. Okay, so now when I'm at this case, I have actually two boxes. One has 3 in it with a label 3, and other has 1 and 2 in it with a label of 2. And I want to create a new box with label 1, 2 and 3. And now it is actually optimal to either label this new box as 2 or 3. I can label it anything. So let's say I label it 3. Let's say if I'm labeling it 2, then this array will become something like this. This pointer will go here and 3 is pointing to itself. And if I'm labeling it 2, then this will become like this. So 2 is there, but now 3 will point to 2. So 3 will point to 2, something like this. Okay, so let's say we have something like this. Now I'm pointing 2 to 3 now. If we have something like this, okay, now how do we find the label of this box? Let's say we get the third query as find the label of 1. So if we get something like find 1, so I want to find the label of the box that has 1. So I can do this recursively. Find label is equals to find label of 2, then find label of 3 is equals to find label of 3, and 3 is pointing to itself, so we return 3. So these are the queries that we want to handle. But if you do it this way, clearly this can take big offline time, and we want to reduce it. Okay, and this is the main problem of disjoint set unions, and there are two techniques to reduce this time complexity. First is called the path compression, and the second is called union by depth. Okay, and I want to discuss these one by one, just so you understand it. Let's say let's first discuss the union by depth. Okay, so union by depth, because I think it is more easy and intuitive. Okay, so let's say we have 1 is in the box with label 2, then we have 3 here, then 4 is also with box label 2, and 5 is also here, and then we have a larger tree. Let's say 1, not 1, I will use different numbers, so 7, 8, 9, 10. Let's say we have 11, 12, 13. Okay, so we have this big one, we have a big box, and second we have a smaller box. Basically this is only 1 2 3 4 5 elements. 1 2 3 4 5 6 7 8 elements. Now I have two choices. Can either I mean this is pointing to itself, right? So either I can change 2 and point it to here, or the second choice is either I can point 6 to 2. Now which do you think is more optimal? I will give you 5 seconds to think about this, and okay, so kindly think about it. Okay, now I'm assuming you have actually thought about an answer, and let's try to see why one is more optimal. Basically what we want is, we do not want to increase the height of the tree. We do not want to increase the height, because if the height increases, like let's go to the previous page, because if the height increases and I am querying from find 10, then I have to go along this whole height, so this will cost me a big O of n time, right? So this is not something we want. If the height was smaller, then it will cost me less time. So that is why if I have two trees, let's say one has a smaller height and then we have something with a very big height, if I point this to this, so this will make something like this, right? This is here, then this is pointing it like this, so this will become the addition of heights. But if I point it the other way, so if my this is pointing like this, you will see that overall the height is equal to the bigger tree. The height is not increasing, so this is more optimal. I should point the smaller, the tree with smaller depth or height, to the bigger tree. So for this I will maintain an array of heights. Okay, so this will cost me a big of n space, but it will also decrease my time complexity when I try to find the sets. Okay, so that is the case. Then let's discuss the other technique that we have to use. It is called path compression. Now we can have something like this, that one is the label element, 2 here, 3 here, let's say 4 is pointing here, then we have 5 is pointing here. Okay, now clearly, I mean, we can't do much about this. Like if I have 3, it will cost me a big O of n time to reach from 3 to 1. But what we can do is we can reduce it to, we can't actually reduce this to O of 1, but we can reduce it to amortized O of 1. Basically what we do is, from 3 we go to 2, we remove this edge, we go to from 2 we go to 1 and we remove this edge. Okay, and since 1 was pointing to itself, we know that this is the leader, and then I change these edges from 2, while recursing back, I will change this edge back to 1, and I will change this 3 and point it to 1 itself instead of pointing it to 2, because this edge will not actually matter. So when I query 3 for the first time, it will tell me that okay, it will take O of n, but if I query it to the second time, it will cost big O of 1 operation, big O of 1 time, to tell me what the leader of this set was. So similarly for I can do it for 5. First I will remove these edges, and then when I query for 5, I will add these edges back to the leader directly, and this technique is called path compression. Okay, let's also see some a better example, something like this, 5 elements, and first I say okay, what is find of 3? What is find of 3? Okay, so if you do find of 3, you will realize what will happen is this edge will be removed and it will point directly to 1. Then when you ask what is find of 5, we will go here and directly we will jump from 3 to 1. So we have skipped a node, and after this, when this is over, this will point to here, and this edge will be removed and directly point to 2. So when you do find 3 and find 5, the tree will look something like this. So 2, 3, 4 and 5, and after this, whenever you query, your operation will simply be in big O of 1. So I can average these O of n and O of 1 to almost a big O of log n time, and this can easily be used while competitive programming, and this is the optimal complexity that we want. Okay, so I think the theory is pretty much clear. If you have any doubts, you can comment in the below this video. Now let's also see the implementation. And today I won't actually be coding this because I don't think it is necessary for me to type everything step by step, but I will explain the template code, and I will also share my template down this video in the pinned comments. Okay, so my template looks like this, and I will just show you what this is. First, I'm maintaining 3 arrays. One is the rank, or I can even call this depth, and I'm also maintaining the set size. What this set size is it is basically the number of elements in the set. What if I ask you, what if you get a query like what are the number of elements in the box with label this, and if you get something like this, then it will then for that purpose I am maintaining the set size. This is the union by rank, and this is the parent, or I can say the label of a particular element, like that. And this is the number of DSUs, disjoint sets that I have, so I'm also maintaining that. And I initialize it like initially all the elements will be equal to the label, all the labels of the boxes will be equals to that, right? And the rank and currently all the depth of the trees are initially 0, set size are 1, so every set has only one element, and the number of disjoint sets is n. Now this step is called path compression. I am doing it recursively. Obviously if parent of x is equals to x, then I need to return the x, that means I have reached the label. Otherwise I will say, if I say p of x equals to find x, this will also work, but that is not path compression, right? When I return back from the label, I should reset this value. So that is why so this step is called path compression. And then I also have a same function that, okay, it tells me if these two are from the same sets. Then I have union values. Okay, first thing that I have to do is check if the I and j values are from the same set. If they are from the same set, then I don't need to do anything, I can simply return. Otherwise, first I have to find the labels, and then if the rank is, I want to point the rank of the smaller tree like this to the rank of the bigger element. Okay, so we have this. So if the rank of x is greater, then I swap them, and if the rank is obviously equal, then I should say rank plus plus. Then only the height of the tree increases, otherwise it remains same, and the set size increases obviously, and the number of sets decreases by 1. Okay, now if you want the size, then you can simply return the set size of that number. And we also want to get the number of if you want to get the number of disjoint sets, then you have this. I will put this code in the pinned comments so you can copy it from there, and this is in C++. And I hope you were able to understand this concept, and in the next video I think I will discuss the minimum spanning trees if you want. So kindly comment down if this video actually helped you. So thank you. I will see you guys next time. Thank you.